The spatial wave pattern of an electron in an atom is called an orbital. And we've seen a few examples of electron wave patterns already. And here are some pictures. And the term orbital is short for one electron orbital wave function. And it's a description of an electron wave in an atom. And the it's the wave pattern for the electron is analogous to the energy pattern in something like a vibrating drumhead, or in a sound wave that's in a room, or a light wave. But there are a number of useful similarities between the orbital wave function and the vibrating drumhead that make it a nice comparison. So the simplest type of electron wave pattern that you can have in an atom is similar to the sort of fundamental vibration mode of a circular drum, where the entire thing has energy. There's more energy in the center, and the amount of energy sort of tapers off as you move out to the outside. The one Well, there are a couple of important differences. One being that the drumhead is just two-dimensional, whereas the electron wave pattern exists in three dimensions. Another important difference is that the wave on the drumhead is contained by the rigid boundary of that membrane, whereas the electron wave in an atom is contained by the attractive force between the electron and the nucleus. And so the boundary of that electron wave pattern is a lot fuzzier than the boundary of the wave on a drumhead. But otherwise, the idea that you've got this distribution of energy, and there's greater intensity in the center than there is on the edges, is a useful analogy. And then the second wave pattern that I've got illustrated here would correspond to a different kind of vibration of a drumhead, where you've got strong intensity of the energy in the very center and also in the periphery, but there's a region in the middle where there isn't any, where the wave doesn't have any energy at all. And these kinds of patterns exist in vibrational modes, and they also exist in these electron wave patterns. And such a region of space where the intensity is zero is called a node. And so here we've got a node that's located at a particular distance from the center. The wave pattern on the right is analogous to this kind of motion of a drumhead, where again there's a region where there's no energy, and but that is on the membrane. It's along a line, and in the electron wave pattern, that node is a plane between one side of the nucleus and the other. And again, that's a region of space where the wave has zero intensity. And you may have noticed in pictures like these that they often are drawn with color coding. Most often you'll see them color coded with red and blue, but you'll also see other combinations of colors. And the color coding is meant to indicate a mathematical feature of these wave patterns, and we don't really need to be concerned about that. For us, the color coding is useful because it emphasizes that there's a region where there's a node in between where the wave intensity goes to zero, and that's kind of emphasized by using contrasting colors. So these electron wave patterns are described by a set of quantum numbers. So we saw when we discussed the Bohr model of hydrogen, in the Bohr model there was one quantum number that was called n. These orbitals, these orbital wave functions, need three quantum numbers to describe them. And of those, the most important is the principal quantum number n, and that determines the energy level, just like it did in the Bohr model of the hydrogen atom. And in fact, the pattern of energy levels in the quantum model of hydrogen is identical to the energy pattern in the Bohr model. And this really shouldn't come as a surprise, because the Bohr model was created to describe the observed spectrum of hydrogen atoms, and so the pattern of energies that matches that spectrum is going to be the same for the Bohr model as it is for this new quantum model. And the expression for the energy, that the energy of the nth level is negative k divided by n squared. That's the same expression that we saw in the Bohr model, and that constant, 2.179 attojoules, is also the same. And again, we've got this pattern where the energy levels get closer together as you go up in energy. And if the electron ever gets enough energy that it reaches the zero level, then it actually escapes from the atom, and that process is called ionization. So within a particular energy level, you can have several different types of orbital wave functions. The simplest type of orbital is referred to by the code letter S, and the S-type orbital is the S actually comes from the word sharp, which was used to describe atomic spectra. But if it helps, you can think of the S as standing for spherical, because S-type orbitals have a spherical shape. They look the same from every direction. The next type of orbital wave function is called a p-type orbital. The letter P comes from the word principal, which again comes from descriptions of atomic spectra. As far as we are concerned, it's just a code letter that refers to this type of wave pattern. And then beyond that, there is another type of orbital called D, which comes from the word diffuse. And beyond that, there is another type of orbital called F, which comes from the word fine. And these different types of orbitals belong to what are called sublevels within an energy level. And the number of sublevels in an energy level varies, and we'll talk about that momentarily. And as far as we are concerned, all that we need to understand is that there are these different types of orbitals, and that their letter codes are S, P, D, F. There is the physical difference between these types of orbitals is that they differ in the amount of rotational kinetic energy that the electron wave has. A wave pattern around an atom has kinetic energy and potential energy, and these different orbital types, they differ in how much of their energy goes into rotation of the wave around the atom. Looking at the different energy levels in an atom, the first energy level only has the S sublevel, and there's one S orbital. In the second energy level in an atom has two sublevels, the S sublevel and the P sublevel. There's enough energy in that level to be able to form waves of either type. And again, in the S sublevel, there's only a single orbital wave pattern. In the P sublevel, there are three different wave patterns, and they're commonly drawn as being oriented along the X, Y, and Z axes. Although there are different ways to draw them, this is the most common way that you'll see them visualized. The third energy level has even more energy, and it is able to exist in three different sublevels. So you've got the S sublevel, the P sublevel, and now there's enough energy to have a D sublevel. And as before, there's one orbital in the s sublevel of the third energy level. There are 3 orbitals in the p sublevel, and there are 5 orbitals in the d sublevel. And you can see I've shown the standard picture representations of those orbitals. Again, we don't need to be super concerned with the patterns in those pictures, although they are kind of fun to look at. And then going even further, in the 4th energy level, again, there's even more energy available, and there are 4 sublevels. And so you can have there's a single s orbital. There are 3 orbitals in the p sublevel. There are 5 orbitals in the d sublevel, and there are 7 orbitals in the f sublevel. And you may notice that there's a pattern here that as you go from one sublevel to the next, the number of orbitals in that sublevel is just the next odd number. So there's always 1 in the s sublevel, there are 3 in a p sublevel, there are 5 in a d, there are 7 in an f. And this pattern does continue. In the 5th energy level, you have all of these sublevels along with a g sublevel. So the pattern does continue, but these s, p, d, and f type orbitals are really the only ones that we need to worry about. So these different types of orbitals describe the spatial pattern of the electron wave. And but there is one other property of an electron wave that's not that doesn't show up in these spatial patterns, and that is something called electron spin. Electrons are said to be spinning either clockwise or counterclockwise, and that term is kind of misleading because it kind of gives the impression that an electron is like a tiny little planet that's spinning around on its axis, and that's not really accurate because an electron isn't really acting like a particle. It is behaving as a wave, and so it doesn't really make sense to say that it's spinning the way that a planet does. The reason why this property of electrons is called spin is because if you have at a macroscopic level, if you had electrons in, say, a wire, if that wire is spinning, that will create a magnetic field. And this electron spin refers to the fact that electrons in atoms act like tiny little magnets, and the magnetic field of an electron, the North Pole can either point up or down, and so that's analogous to saying that the electron is spinning clockwise or counterclockwise. And as far as we are concerned, the only thing that matters is that there are 2 different possible spins, and that an electron can have, can be in, it could be in either one of those states. So coming back to the diagram of the energy levels, it's very common to represent the orbitals and the sublevels of an atom with boxes, where each orbital is represented by a box in a picture like this, and you can see they are arranged by energy level, and within each orbital there are 2 possibilities for an electron. So you can have an electron with its spin going up or with its spin going down, and that's traditionally represented by using a little arrow. And so one direction for the electron spin is represented by an arrow pointing upward. You could also have an electron with the arrow pointing downward. And those are 2 different possible wave patterns for the electron. The spatial pattern is the same, but the only difference between the up arrow and the down arrow is just the direction of the North Pole for that little magnet. And so, this is how you would represent it in this kind of picture. And if you've got something like a hydrogen atom, If the electron were to make a transition from one energy level to another, for example, if the atom were to absorb a photon, um, then the electron will just go from one orbital to another. And likewise, if an electron drops from a high energy orbital back down to a low energy orbital, the atom can emit a photon. And so this gives us sort of a way to picture the electron in a hydrogen type atom. And in the next video, we're going to look at what happens or how we apply this quantum model to more complicated atoms where there's more than one electron. But again, that's the story for next time.